Hello, good morning students. In the previous video we have discussed the numerical problems connecting the mirror formula and the linear magnification. In this particular video we discussed the image formation by convex mirror as well as the third property of light, that is a refraction of light. So image formation by convex mirror. Here M dash is the convex mirror. Concave surface is silvered and painted, and the convex surface is a reflecting surface. When the object is at infinity, the light coming from the object is a parallel beam of light. When this parallel beam of light parallel to the principal axis made to incident on the convex mirror, after reflection all reflected light rays appear to diverge from a point on the principal axis called principal focus. If the object is at infinity, the nature of the image formed at principal focus is virtual, erect, diminished image is formed at a principal focus behind the convex mirror. So in the rear view mirrors, if the bus is coming from behind our two-wheeler, the bus or the car appears to be erect, small in size and very close to us. So the nature of the image formed in a convex mirror is virtual, erect, diminished image is formed at a principal focus when the object is at infinity. The second case, if an object is placed very close to the mirror in front of a convex mirror, then a set of rays we consider to get the position and the nature of the image. A ray parallel to the principal axis, say BM, after reflection diverges and appear to diverge from F. A ray directed towards the center of curvature falls on the mirror normally, then it retraces its original path but in opposite direction. A ray incidenting at the pole, suppose the angle of incidence is 30 degree, that is the angle between BP and AP, that is the angle of incidence 30 degree. Then after reflection the light advances in that particular direction such that the angle of reflection is also 30 degree, or angle of reflection must be equal to angle of incidence according to the second law of reflection. All the reflected rays, when they are produced backward, they intersect each other at a point. Through this point of intersection, a perpendicular A dash B dash from the principal axis is drawn, which gives us the position and the nature of the image. So if an object AB is placed in front of a convex mirror M dash, the nature of the image formed is virtual, erect, diminished image is formed behind the mirror, that is between P and F. As we know, in the first case, when the object is at infinity, the image will be formed at F. When the object is just in front of the convex mirror, the image will be formed between P and F. Here A dash B dash is the image form. The nature of the image is virtual, erect, diminished image is formed behind the mirror. Uses of concave and convex mirrors. Concave mirrors are used in torches, searchlights, solar cookers as reflectors. Convex mirrors are used as rear view mirrors in vehicles. Further, we need to discuss the third property of light, that is a refraction of light. The first one is a rectilinear propagation of light. The second one is a reflection of light. The third property of light is a refraction of light. It is the phenomena of a bending of light at the interface when light travels from one medium to another medium. And this bending of light at the interface is due to decrease or increase in the speed of light as the light enters from one medium to another medium. Whenever the light traverses from one medium to another medium, at the interface, after bending, the speed as well as the wavelength of light changes, but the frequency of light remains same. Speed of light in air is slightly less than that in vacuum. Number of experiments were conducted to determine this very important quantity of light, that is the speed of light in vacuum, which amounts to 2.99 into 10 raised to 8 meter per second, but it is approximated to 3 into 10 raised to 8 meter per second. In practice, speed of light in air or vacuum. Actually, in air, the speed is bit less as compared to the speed of light in vacuum, but for all practical purposes, in practice, we take the speed of light both in air and vacuum as 3 into 10 raised to 8 meter per second. When the same light traverses from air medium to water medium, the speed of light decreases. The speed of light VW is 2.25 into 10 raised to 8 meter per second. Also, when the light traverses from air medium to glass medium, the speed of light in a glass medium Vg is given by 2 into 10 raised to 8 meter per second. As optical density of the medium increases, the speed of light also decreases. So velocity or speed of light in water is less than that in air and vacuum. Velocity of light or speed of light in glass is less than that of in water. So in other words, glass is optically denser than water medium. Water is optically denser than air and vacuum. So the bending phenomena of light traveling from one medium to another medium is called refraction of light. So we need to discuss the laws of refraction. Refer to the ray diagrams here. XY is the interface, that is the surface separating the two media. Medium 1, optically rarer medium, let it be air medium. Medium 2, optically denser medium, let it be glass medium. Light ray AO incident obliquely on the interface XY at an angle I. At the interface, the light, instead of going straight, it bends through an angle. The angle through which the light bends is called angle of deviation. Light traversing from rarer to denser medium, after refraction it bends towards the normal. If a light is advancing from denser medium to rarer medium, after refraction the light bends away from the normal drawn at the point of incidence. Here NO dash is the normal drawn at the point of incidence, that is O. R is the angle of refraction. R is the angle of refraction. For light traveling from air to glass, rarer to denser, angle of refraction is less than angle of incidence. For a light traveling from denser to rarer, AO is incident ray, OB is refracted ray. So at the interface, the light bends away from the normal here. Angle of refraction is more than angle of incidence. The difference between the angle of incidence and angle of refraction is called as angle of deviation. In other words, the angle through which the light bends. Here I is greater than R. Angle of deviation D is I minus R. When in the case light bends away from the normal, angle of incidence I is less than angle of refraction, or angle of deviation is r minus r, angle of refraction minus angle of incidence. Whenever the refraction of light takes place, it takes place according to the two laws of refraction. The first law is the incident ray AO, the refracted ray OB, and the normal drawn at the point of incidence NO N dash all lie in the same plane. If interface is in the horizontal plane, then all these incident ray, normal, refracted ray, they all lie in the vertical plane. That is the first law of refraction. The second law is for a given pair of media, air glass, air water, air diamond, water glass, and for given color of light or a wavelength of light, it is the ratio of a sine of angle of incidence to the sine of angle of refraction is always a constant for a given pair of media and a wavelength of light. That is, sine I by sine R is always a constant. That equals to, we write n to 1. Light travels from first medium to second medium, and here n to 1 is called as refractive index of medium 2 with respect to medium 1. And this second law of refraction is also called as Snell's law. Let me define the Snell's law. For a given pair of media, for a given wavelength of light, the ratio of a sine of angle of incidence to the sine of angle of refraction is always a constant quantity denoted as n to 1, which means refractive index of a second medium with respect to first medium and refractive index of second medium with respect to first medium. In other words, refractive index of a glass medium with respect to air, since the light travels from air to glass. Thus, the refractive index of glass with respect to air, that is medium 2 with respect to medium 1, n to 1, is a sin I by sin R. Note number 1. Snell's law is invalid for normal incidence since the light travels undeviated. If light incidents on the interface normally instead of obliquely, then the light doesn't bend, it travels undeviated. In that case, angle of incidence is 0, angle of refraction is also 0 since light travels undeviated. The Snell's law is invalid for normal incidence. The second one, refractive index of a denser medium with respect to rarer medium is always greater than 1. That is, since I is greater than R for light traveling from rarer to denser. Whereas N12 is less than 1. For light traveling from denser medium to rarer medium, light bends away from the normal. Angle of incidence is less than angle of refraction, and if you take the ratio of sin I by sin R, we will get the refractive index of first medium with respect to the second medium, that is a refractive index of air with respect to glass, which amounts to be less than 1. Refractive index in terms of speeds of light. Refractive index also can be calculated if you know the speeds of light in both the media. Absolute refractive index of water with respect to air, which means light travels from air to water, then NWA is a ratio of a speed of light in air to the speed of light in water, which comes out to be 1.33. So whatever be the angle of incidence, the refractive index of water always comes out to be 1.33 with respect to air.